So this stack, it's from local Docker development to production deployments. You can see like almost as seen as reInvent. This was delivered to reInvent, but in a slightly different version. It's different, so the version I gave at reInvent was 1 hour long. This one will be only 45 minutes, otherwise the next speaker is going to try to kill me. If you want the version that I gave at reInvent, it was a little bit different. You just Google for DVO 317, and there is a video of that, and it's great. When I did it at reInvent, there were like 2 projectors like this, and 1 projector went down, so half of the room was like that. So this time, hopefully, everything should be fine. So this version is slightly changed. Like I removed most of the demos to talk a little bit more about how things work, because most of the feedback I got from reInvent was that guy is crazy, that was way too fast, and what's going on. You might get a little bit of that impression this time too. So if that happens, don't panic and just refer to the video of the reInvent talk, where you can like slow motion and replay and pause and everything if needed. All right, so intros, I'm Jerome Petazzoni. I work for Docker, and before Docker was Docker, it was .cloud, and I joined .cloud almost 5 years ago. So that gives me 5 years of experience with containers, so that's great. When random recruiters tell me, hey, we're looking for someone with 5 years of Docker experience, I can say, yep, I got that. And so, yeah, at Docker, I do lots of talks like this one, but I really like to put things in containers. We are trying to create a kind of union or kind of secret thing with Jessica Frazel, where we put things in containers and we run things with shell scripts as well. But that's a different story. That's not what I want to talk about today. What I would like you to imagine, if you already saw me talk about Docker, is forget about it, and instead of pretending that I'm like the Docker guy, let's pretend that I'm just Jerome. I'm a software engineer about to start a new job tomorrow, and I will start in a company called like Docker Coins. They do some cryptocurrency, blockchain, whatever. I don't know much about it. They asked me if I could join the company to scale their stuff on EC2. They just told me they were using Docker everywhere. They don't know much about cloud. When we did the job interview, I could tell the difference between EC2 and S3, so they give me the position. But I don't know really much about it, and so the only thing they told me about their stack is it's all on Docker. You will see it's ridiculously easy. The only thing you have to do for your first day is to install the Docker toolbox, and we will figure everything out like on the spot. Fine. So before my first day in this company, I installed the Docker toolbox because that's the only instructions I got. And installing the Docker toolbox is basically like Googling Docker toolbox, going to the first page you find, and downloading and installing it. And so once you have that up and running on your machine, so it's like 5 minutes, well, more if you have slow internet, basically the first thing that you do is you try to get the stack up and running. And so the instructions that like my new engineering manager gives me when I start my new job in this company is all you have to do is git clone the repo, then run docker compose up, and that's it. The app will be up in your browser, you can access it, and that's it. A little bit like with Vagrant up, and boom, things work. So here, in the other version of the talk, I did a small demo of that, but here I want to kind of cut to the chase, and I expect that lots of you have already probably used Compose anyway. And so, yeah, if you redo that, you clone that repo, you do compose up, and you get your full application up and running on your local machine. That's great. So the way it works, for those of you who haven't done that yet, is that Compose will look at Docker Compose YAML file, which contains a full description of my application. That's so, for instance, for a small web application, it looks like this. There is like a web section, and then there is a Redis data store. For a more complex application, it might look like this. So here, I have like 5 services. I have RNG, Hasher, Redis, Worker, WebUI, and for each of those services, I'm telling to Compose either just use a pre-built image that happens to be in the Docker Hub public registry. So that's the case for Redis. Just run the Redis that was made by someone and put online on the Docker Hub. And then for the other services, I have a build keyword, which means in that directory, you have some source code and also a Docker file, which is a recipe explaining how to build that container. And so when I do Docker Compose up, it will build all those containers that have to be built, and then it will run everything together. That's pretty much it. So the sample app that I've been using for the demos at the reInvent talk are all available online, and so all the things that I'm talking about here, you can check them out for yourself and test them if you're so inclined. So even though I'm not showing the demo to save some time, this stuff actually works, believe it or not. So there is like this Docker cons repo. So it's a microservices architecture. So you slice and dice down your app into small bits, each potentially using a different language and framework. You don't have to use different languages and framework, you can, but just because you can doesn't mean you should. And so you get all that stuff up and running. In the sample app, I deliberately picked completely different languages and frameworks just to prove the point. So there is like a web service in Ruby and Sinatra, another using Python and Flask. The front end is in Node and Express. I had to actually learn Node and JS to write that. That was a pretty traumatic experience. But I did it and it worked. And so that's, and there are many different services like background workers, web services, web UIs, and even like a stateful data store. So, well, that's the mandatory microservices are good. You should eat some of them for breakfast plug. Well, just one thing, because everybody probably tells you all the time that microservices are great. I just want to tune it down a little bit and also give you some of the drawbacks of microservices. When you use microservices, suddenly your application turns into a distributed service, and distributed services are among the hardest thing in the world. If you don't believe me, just Google for Afir, Jepson, Call Me Maybe, and read those blog posts, and then you will understand why distributed systems are hard, because almost nobody can get them right. You also now need to have load balancing, service discovery, and lots of other components that you could completely ignore when you just had this big monolith or monorail app. Right, so okay, done with the microservices speech. Now, okay, I have this thing that I can, my application, I can bring it up on a single node, but how do I get that on like a remote EC2 instance? So that's almost the same thing. I will provision a Docker host using, for instance, Docker machine, and then I will log into that Docker host, and I can git clone, compose up. That still works exactly the same way. Now, where things will change a little bit, so Compose makes a good abstraction of the dev environment. If you are familiar with Vagrant, it's kind of the same idea, except we kind of zero in on containers. So it's like, this is Vagrant, but for containers. So it won't let you, Compose will not let you boot like a Windows app somewhere, but since it's for containers, it will integrate this kind of build process. It will link containers together. So I will explain a little bit later what that really gets us. And so once we have a Docker machine anywhere, on this Mac, on my Linux machine, on some EC2 instance, on Linode, Dio, whomever, physical machine, it doesn't matter. I just have to point my API, my Docker client or my Docker Compose client. I just point it to the API endpoint of my Docker machine, and everything works exactly the same way. Great. But how do I deploy to production and at scale? So before answering the question, let's see exactly what's in this question. What are we missing to have a deployment at scale in production, something that we can send actual traffic to? So we need a cluster. So for that, we need to provision that cluster. We need some way to build our code and manage the life cycle of the code, which means if today I make a release and tomorrow I make another one, I need somehow to kind of keep track of that. And at some point, if I want to go back to how things were before, I want to be able to do that, so to know exactly what I deployed, not just YOLO some code and hope for the best. I need to do service discovery, and I probably need tons of other things like backups, logging, security, and so on and so on. But for this talk, since we don't have that much time, I want to just talk about those. Right, so provisioning a cluster. Here I will show, well, not exactly show them because I decided to scrap the demos, but I will talk about two ways to provision a Docker cluster. If we look at like the traditional ways to provision clusters on EC2, and you can map that to pretty much any other kind of cloud, You can do some manual instance creation. Like you go to the web interface and you click, 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 and boom, you get your machine. You can use the CLI, which is slightly better because once you have something with the CLI, like AWS, EC2, run instance, blah, 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 then you can put that in a script. And scripts are good because they are like the first step toward automation. You can use auto-scaling groups, which are this nice EC2 feature that gives you a big like kind of knob that you can turn like one way or the other to get more instances like this one or less instances like this one. You can use CloudFormation templates that are even better if you need not only EC2 instances, but other things like load balancers and RDS databases and whatever. Or there are two methods that are kind of specific to Docker, using Docker Machine and using the ECS CLI. So those are the two that I want to talk about a little more in depth. So Docker Machine is a tool that comes with a Docker toolbox. So in the beginning, when I downloaded and installed that Docker toolbox, I not only got Docker and Docker Compose, but also Docker Machine. With Docker Machine, I can create Docker hosts on pretty much anywhere, like locally on my VirtualBox thing, if I want more Docker engines for some reason, on some remote cloud. If I have a bunch of machines and I want to control them for Docker machines, it's also super easy to do. So that's great. It can also integrate with Swarm. So for those of you who tried, like in the early days of Swarm, to set up Swarm, on the beginning it was really hard because you had to create SSL certificates using some special OpenSSL flags and everything. This is like a thing of the past now because Docker Machine automates that and makes it super easy. And however, now let's talk about the downsides, the limitations, the current limitations of Docker Machine. For now, you can only create one machine at a time. So if you need a cluster of 100 machines, you have to write a for loop. And also, it's using centralized credentials, which means that if I'm creating my cluster from this machine, then if you need to access the cluster, you have to be on this machine. So you can kind of work around that with Bastion host or by copying credentials afterwards, but this is something that we definitely know that we have to improve. So that slide should not be there. So let's blame Office. And so this is how we create a cluster with a machine. So we create a token, so that's something for Swarm service discovery mechanism. And then, like literally, if we were to execute those 10 lines, we would get a 5 nodes Swarm cluster on EC2, and it would take roughly 3.5 minutes. So that's pretty simple. Okay, for those of you who are not familiar with shell or whatever, it's like, okay, what is this code? But trust me, this is really simple compared to what we usually have to do to get a full cluster up and running with some scheduling orchestration mechanism on top of it. Now there is the ECS CLI. So the ECS CLI is something that was released at reInvent a couple of months ago, and it was kind of one of the big axes for that talk. And the ECS CLI, for those of you who were at DockerCon San Francisco in June, or maybe you heard about it, but basically somebody from AWS said, and we are going to integrate with Docker stuff. This is what they were talking about. This is a small CLI in Go that allows to do like state-of-the-art Docker stuff on Amazon. So for instance, with the ECS CLI, when you create a cluster, it will use a CloudFormation template. It will automatically put that in an auto-scaling group. It will integrate with IAM. So some of the complaints that people could have about Docker Machine are gone because, okay, now instead of doing a for loop, if you want more machines, you just like set the number of desired instances in your auto-scaling group, and that's it. For credentials, access, and everything, if you have users in IAM, you can use that. So great. So with ECS CLI, creating a cluster looks like this. So in theory, you just have those two ridiculously simple commands to do, like ECS CLI configure and ECS CLI up. The reality is that you still have to add, for any practical purpose, an elastic load balancer, so an ELB, an ASG, and set up DNS, and a lot of other 3-letter acronyms to confuse you. But at the end, you get something that works and that is really easy to scale up and down. Great. So we have two ways to stage up a cluster. In one case, we end up with Swarm on this cluster, and in the other, we end up with the ECS management control plane. So now, how do I build and deploy my code on those clusters? So the building with Docker, well, we will just continue to use Compose because Compose was good at building stuff and running it on a single machine, but for the build it was just perfect. So we're going to use Compose to make a build, and then we will take that build, and instead of running the containers, we will set them aside. So we will kind of stamp then this is the build version XYZ, and we will set them aside on either like the Docker Hub, which is like the public hosting mechanism for Docker images, or in DTR, which is the commercial equivalent. So it's like, you know, the same way that there is GitHub and GitHub Enterprise, like GitHub hosted by GitHub and GitHub Enterprise on your own servers. There is the same thing for hosting Docker images on Docker Hub or DTR. And if you don't want to give any money to Docker, even though you should because they are paying their salary, then you can use the open source community version of the Docker registry and like operate it yourself and run it yourself. Everything is fine. AWS also announced theirs, so I don't know exactly where the status is for that, but you could also use that, for instance. Okay, so the plan when we want to make a build looks like this. When I want to do a release, like to run my containers on my cluster, I build everything with Compose, so Docker Compose build. Then I retag my images, so I do Docker tag like this www container will now be jpetazzo / my app www colon this git hash or timestamp. Then we push everything to the registry, and we generate a new Compose YAML file where instead of having build, I have image, referencing the image that I just put to my registry. And obviously you don't do that manually, otherwise it would take like 20 minutes each time you want to release something. You write a script. Speaking of which, all the techniques that I talk about here, I've implemented those for the demos that I did at reInvent with simple Python scripts. Each of those scripts is like 60, 70 lines of code. The idea was not to give you like this is the reference implementation and how you should deploy stuff with Docker or whatever. It's more to say this is how I do it in a way that it's simple enough so that you can borrow it, steal it, rewrite it in Ruby because Python sucks or vice versa, and just kind of own it, not just use that script because that guy said that it was nice to use it. So all those scripts are available in open source, and yeah, and they are on this repo, but don't panic, I will show all the URLs at the end again. All right, this is really small, I do apologize, but it's just to show like the before after when you use the build tag push, and you can see, for instance, that here RNG, I had build RNG, and instead now I have image, jpetazzo, docker coins RNG, and a timestamp. So now I get a Compose YAML file that doesn't need to do any build because it only references images somewhere. Okay. So I have a way to kind of keep my build artifacts somewhere and reference them later, because now I can just keep like that YAML file on the side and say this is the YAML file that describes the deployment for that exact build with those exact images, and keep that forever. And as long as I don't wipe out my registry, my container images are there forever as well. Now, how do we do service discovery? And before talking about how, let's talk about why. Why do we need service discovery? Service discovery is when you have services that need to talk to each other in your stack. So service A needs to talk to service B. And the problem that we want to solve is how does service A know how to talk to service B? Like what is the IP address or the host name? What is the port? What are the credentials? If there are credentials like user, password, database number, database name, whatever. And what if I have multiple instances of B? Like because I'm doing failover, so I need to know which one I should connect to, primary, replica, or maybe I'm doing just like load balancing, I have multiple copies of the same thing, so I need to find a clever way to spread traffic. What if the location of B changes over time? Because I'm doing, again, like failover, so before you wanted to connect here, but now you need to connect here, or because I'm doing scaling, before you wanted to connect here, here, and here, but now we also added there, and there, and there. We need to look that up, and we also need to look that up over time. So I'm going to give two views of service discovery. First, service discovery seen by developers, like how this is not one of those funny Photoshop things where it's like developers seen by other people. It's more like how, as a developer, how will I interact with service discovery? As a developer, all I know is code, so to speak. So what does my code look like depending on how I implement service discovery? So here, the most basic thing we could do is hard-coded service discovery. Like on my local machine, when I want to connect to MySQL or Redis or some API backend, and here I try to not make too much enemies at the same time. So I have like a PHP MySQL example, I have a Ruby and Redis example, and I have a Go and some TCP service example. In my dev setup, I just connect to the address that I happen to use locally, so like localhost for MySQL, and maybe for Redis I'm using a non-default port for some reason, and maybe I'm running the API on port 8000. So I do that. But then my friend is using something different. My friend decided to use VMs for everything because VMs is the future, anyway. And so my friend decided to have different IP addresses for each service. And so here things are different. And my friend also doesn't like default ports for some reason, but instead of doing like me and picking 16379, my friend decided to pick 6380. And same thing for the API. My friend decided that 8000 was no fun and 8080 was better. So now we have two different config files. And when we go to production, we have yet another config file where this time with the MySQL parameters, we have some user and password. Same thing for Redis. So this, each time I go from one environment to the other, I have to change my code to update that. Obviously, I would like to say nobody does that, but unfortunately, I think some people do that. But hopefully, most of us, when we do hard-coded discovery, just have like config files, and you just like switch config files, and that's way better. But even with config files, that's error-prone, because when you go from one environment to the other, you have to make sure you're using the right config file. Otherwise, guess what happens when you're doing some tests in your local environment, but you're still using like the pre-prod or something configuration file, and your code talks to the wrong database. What happens is problems. Maintenance is also expensive, which means each time you add a service, instead of just adding the service to your local configuration, you have to add it everywhere, in every single config file. And sometimes you don't know what you should put, like, oh, we are adding a new API backend, so I'm going to put that on port 8888 on my machine. But I don't know what the other people would want to pick. I have no idea what the ops people will set up in production. So you end up with some kind of half-finished stuff lingering around. That's not great. So another idea is to use the 12-factor app principles, where basically you say we put everything in environment variables. 12 factors says a lot of other things, but on the side of service discovery, it says use environment variables. And so in that case, your code looks like this. Instead of putting like the host name and ports and everything, we access the environment, and that works pretty well because every single language, even Java, has support for environment variables, so everything works fine. The code is a little bit less nice, but that's okay. At least you only have one version of the code. We are not like shuffling around config files. Great. And also, that makes me particularly happy because that's probably the first time that I saw environment variables that were used to describe variations in the environments, because usually we use that for other purposes. So you still have to maintain config files, even if it's in a different way. Like you have a file that contains all the envars for your dev environment and then the other dev environment. The nice thing is that if you're deploying on some platform, you can have this config file kind of on the platform. Like if you are on Heroku or some PaaS, you can like set those envars, and they will be usable by the remote application, and you don't have to commit them in your repo, so that solves a lot of kind of uncomfortable problems about, we're going to have credentials in the repos, I don't like it, my security manager is going to kill me. So we kind of reduce the risk of dramatic errors like credentials committed to public repositories. Then another way to implement service discovery is to use a configuration database, so something like Zookeeper, for instance. And here I used Zookeeper, for instance. And so basically the idea is that when you need to connect to something, instead of like looking up in the environment, you connect to Zookeeper, and then you look up in Zookeeper, hey, what's the address for the MySQL server? So that's the example I've put here. We're connecting to Zookeeper, and we are getting the configuration keys from Zookeeper. So as you can see, the code is less and less nice, and more importantly, that code doesn't deal with one important thing in config databases, which is that you should watch the config database for changes. The point of using a config database is not just to put things aside, it's to be able to react dynamically to changes. So basically, we should have so in Go, that would be a Go routine. In Ruby, there would be some kind of thread. In PHP, I don't know, that would look at what's going on in Zookeeper, and when the key changes, it would update the configuration on your side. And as you can guess, the code then becomes extremely more complicated. So there is another problem with config databases, is that if you decide to use that, then if you want to have exactly the same setup in dev and prod, then it means you need Zookeeper in dev. And then unless you're extremely masochistic, that's going to be not a very nice experience. And so instead of maintaining flat config files, now you're maintaining fixtures like lists of configuration keys that you inject into Zookeeper when you go from one environment to the other. So that's not so great. And all I said about Zookeeper holds exactly the same if you are using etcd or console. So using a config database is like great on paper. You can do tons of really awesome things with it, but operating it is kind of painful. And not only operating it, but even like just for the dev side of things, changing your code to deal with the config database. Then there are some kind of ways to kind of work around the issue. There are some people who had this idea of saying, hey, what if we pretended that everything is running locally? So I want to connect to MySQL, okay, localhost. Redis, localhost. My API thing, okay, localhost, and let's say 8001, and because if I have multiple API backends, there will be 8001, 8002, and so on and so on. In dev, I run everything locally, so that's easy. In prod, locally, instead of running the actual MySQL or Redis or API backend, I'm going to run something that sends traffic towards the actual service. A good example of that is Airbnb Smart Stack, where basically it's an HA proxy that listens locally and accepts connections and routes them to the right spot. And then there are a couple of services to discover where is my MySQL server, for instance, and automatically configure my local HA proxy on all the machines that need to connect to MySQL, so that when I move my MySQL from one place to the other, automatically all those HA proxies reconfigure themselves and magic happens. So that's nice, because now the code can be the same in dev in prod, just like with 12-factor ideas. The deployment will differ a little bit, since in prod I have this extra load balancer, but we are stepping into a world that's kind of nice, because in dev I only have a limited set of things. In prod I have a few extra things, but I don't really have to account for them when I'm in dev. In dev I don't know what I'm going to connect to. I'm connecting to localhost 3306. That's going to be MySQL. And the fact that really it's not MySQL but HA proxy sending my traffic somewhere else, I don't care. It doesn't change a single thing for me. So it kind of nicely separates the work between people writing the code and people running the code. Right. Could we do all that thing like without changing the code and with having like this kind of ideal code base where if I want to connect to my database, I connect to DB, like I want to pretend that there is something in DNS so that DB resolves to the IP address of my database. I want to pretend that there is something called Redis in my DNS so that Redis resolves the IP address of Redis, and so on and so on. The answer is yes, we can do that with the ambassador pattern. And that's exactly what a code base using ambassadors would look like. So in dev, our stack will look like this. So I have that's the components of the Docker Coins application that I was showing earlier. So I have those 5 components, and they are talking to each other. And so on my machine, I have like in /etc/hosts, I have aliases for all my components, so that, for instance, when the worker component is trying to connect to Redis, it will resolve to 172.170.3, which is the IP address of the Redis container. Great. Now, if we go to someone else's environment, maybe they are using different IP addresses, but we don't care. We just update /etc/host and everything behaves the same way. The nice thing is that Docker Compose configures links, and Docker links are exactly that. Docker links are a feature, so you can say those 2 containers are linked together, which really means there is an alias for the name of that container and with the IP address of that container in etc host in the other container. So that basically my worker container can ping Redis and it resolves to the Redis container IP address. Now, how do we deal with running on multiple machines? That's where the actual ambassador pattern kicks in. The idea is that instead of connecting to the actual service, I'm connecting to the ambassador, which for me behaves exactly like the actual service. I'm connecting to Redis. I don't care that Redis is actually not a Redis container, but it's just an ambassador, because it will automatically forward my traffic to the actual Redis. So here I have like my app is fully deployed on 2 nodes. So the nodes are the big orange squares, and then the blue boxes are the containers, and the gray boxes are the ambassadors. And the ambassadors can also deal with load balancing. Like you can see, I'm going to go to the other side this time. Like when worker connects to RNG, RNG is not the actual RNG service, but a load balancer that will dispatch traffic across the 2 RNG instances. So the ambassador not only takes care of routing traffic, but also can load balance it and could even deal with failover and things like that. All right, so now if I use that, my code remains readable and clean because I'm not connecting to Zookeeper and then looking up something and whatever. No, I'm just connecting to that name and that's it. Plumbing is abstracted away because when I'm running on my local machine, I just have those 5 containers and nothing else. But in prod or in a more complex testing environment, I can have more containers, but I don't have to know about that, and I don't have to change my code just because somebody decided that now we have load balancing for that component. So again, nice separation between things. Now, some of you might wonder, hey, what about overlay networks? Like this new feature that landed in Docker 1.9 and that has been around like in the experimental branch for ages. So first, what is an overlay network? Because, I mean, I would like to ask, so who knows about overlay networks? I see a few hands, so yeah. But so for everybody, an overlay network, I like to say that it's a kind of a multi-point VPN, but without encryption. But really, it's just a virtual network that spans over an existing network, hence the name overlay network. And so I'm interconnecting my containers using that overlay network, and that overlay network is using a base network. Sometimes they talk about underlay network, and this network is like the basic simple IP network that my Docker host already have. So again, it's a little bit like a VPN, except generally you don't put encryption because you want super crazy performance, and it's kind of multi-point. You don't have like this one VPN concentrator. No, it's kind of distributed in the way it works. It often relies on broadcast or multicast, which is not available on EC2 and most other cloud platforms, or some distributed store. So the kind of the flat note for overlay networks is that if you want to run on cloud, now you have to operate a distributed store. But let's put that away for a bit and let's see what our app with an overlay network looks like. So now I have all my containers. They are on multiple machines and they can talk to each other automatically. Problem solved. Let's go have beers. Except, nope, because if I have multiple like scaled components, like here I've put like 2 RNG backend services, what's going to happen here? I still need a load balancer. I still need somehow to kind of spread traffic across the two things. So I still need a load balancer. Just because I have an overlay network, it doesn't magically remove all the problems. And sometimes things will really suck because I will be like this. Like I will have the load balancer somewhere else, and basically if my worker service makes requests to the RNG service, sometimes the request will go to the other machine and then back to the original machine, and I will have a crazy high latency compared to what I could have if I were connecting locally. So this is not good. So if I'm using an overlay network, my code remains readable and clean. Plumbing, for trivial scenarios, I don't need to do plumbing because it's okay, my containers can talk to each other. But if I'm doing load balancing or failover between containers and things like that, I still need to have extra plumbing. In some scenarios, you can get away with DNS round robin. So in that figure, actually, RNG would resolve to both IP addresses, and I would sometimes talk to the local instance, sometimes to the remote instance, and it wouldn't be that bad. Okay, so now let's talk about service discovery, but from the other side, so from the ops side, like I'm ops and I have to implement service discovery. What can I do? So here I decided to make kind of 3 categories depending on how fast we are moving. So how fast are we moving? First, if we move slowly, so basically if we deploy once a week or once a month, like the deploy is a kind of special event. It's okay to have a few minutes of downtime because we can schedule that to be like in the weekend or maybe the middle of the week in the night or something. So that's okay. Failures are pretty rare. Like we have one database problem once a year or maybe even less than that. Or if we have more failures, they don't have a critical impact, so that's okay. And when we do reconfigurations, like, oh, we move the database to a bigger server or we scale up, then it's not urgent, basically. When we need to make that, okay, we need like more servers, we will deploy them next week, and we will put them in the load balancer configuration in the deploy of the week after. So that's 2 weeks to scale up, okay. If that's if those are our requirements, that's not too hard. The easiest solution is you can bake your service discovery into your build so that in your containers, like in your code, you have a small file that describes all the parameters. And so when you need to change things, well, you just build again, repush again, and everything is fine. So the result of that is that there is kind of zero investment to get there. You just like put your service discovery information in your code and that's it. It's pretty easy to understand, except when everything is broken and you're like, okay, we need to fix things, but the only way to fix them is to push again, then the next push is next week. So let's stay down for 3 days, if that's okay. And the drawback is that each deployment carries a lot of risk. Because it's like, oh, this is the deployment window. It's deploy Wednesday, so there is code freeze Tuesday, and then maybe feature freeze Monday or something. So that's really not agile. Now let's see another scenario where we're moving a little bit faster. So now we deploy every day, like every day at noon, boom, deploy, deploy, deploy. We can't accept downtime, except maybe a few glitches, like, okay, we deploy at noon and during like 20 seconds, there was some people will get like 500 errors or something like that, and it's like, it's not awesome, but we can live with it. Failures happen regularly because we have hundreds of machines, and so statistics. So we have machines crashing, maybe not all the time, but regularly. So we have to have a good plan B when something goes wrong. And reconfigurations are frequent. Very often we are adding nodes, moving stuff around, changing types of instances. So we need that to be fast. We can't wait 2 weeks just to add one server. Strategies. Here, well, the one that I think capture really nicely is to inject configuration after deployment. So you deploy, then your app is in a kind of not ready state, like, it's trying to connect to DB, but it doesn't know yet what DB is. So, and then you do kind of second round when you inject the actual configuration. And so when you make a new deploy, you still have the old configuration, but you kind of push the button after the deploy to generate the configuration, like update the configuration everywhere. The advantage of this strategy is that when you're changing something, you just have to rerun that script and update all your parameters everywhere. It's relatively easy to understand and implement. That's the strategy that is used in the demos that I did for the reInvent talk. So and it's like 4 or 5 scripts of 60 lines each. So that's okay. Drawbacks is that services must allow reconfiguration. So if you have services that you can't reconfigure, you can't do that. The good news, that's pretty rare, except if you have some crazy in-memory Node or Java thing that loses everything when you restart it, you should probably be able to do that. And you start to have a risk of meta failure, which is a failure in the deployment system, and then you say, oh, we have a bug, but we can't fix it because we have broken our tools. So we need to repair our tools first before we can fix the other thing. And then there is the scenario where you want to move wildly, like this famous move fast and break things. You deploy all the time, like thousands of times a day. It doesn't mean that you deploy like every minute, but it means that you have many different components, and some of them will be deployed multiple times every day. So n components times multiple times a day times multiple machines, you just multiply everything, and that's how you get like figures like, yeah, we deploy 1 million times a day, yeah, because we have 1,000 component or maybe more across 1,000 machines. So that's how. Downtime in that case is not okay, because even if like one little service is just down for 10 seconds when you deploy, that's not okay, because if one request goes across like 20 microservices, statistically the chance for one of those microservices to be in this little deploy 10-second downtime mode increases a lot. And so now if you look at your overall uptime and error rate, it starts to look not so great. So you need to have something so that deployments are perfect and have zero downtime at all. Now you have also failures happening all the time, everywhere, not because code is crap or servers don't work or something, but just because you have so many of them. So again, statistically, when you have millions of things, you have some of them failing, maybe not every second, but really, really often. So you need to have something fully automated so that when something breaks, you can automatically like move it away from rotation or replace it, or at least know what's going on. So strategies for that, you need to be able to detect changes when they happen. So you need to have a combination between monitoring, between maybe a stream of events telling you what's going on, like machine went up, machine went down, this went out of memory, whatever. You need to have services that either that register themselves automatically somewhere, like when there is a new service somewhere, you have to know almost in real time that this service is here. So either by having the services registering themselves or by doing some fast polling. And then you need to just have some logic that when something happens, you take some action, or when some metric goes above or below a threshold, you take some action, and so on and so on. Results, everything happens automatically. It's nice. You can scale up super easily when you deploy everything. Like it's like perfect. Drawbacks is that you now have lots of extra moving parts, like this whole thing about monitoring your app and having the way to trigger action when something is out of spec, automatically reacting to deploy of new versions to put them in AB or canary deployment. And meta failures now are really dangerous, because the whole deployment pipeline itself is an application or even multiple applications. And so if something fails there, good luck. So ambassadors in action. So here I want to give some ideas of how to actually implement ambassadors and show that it's really easy. So I will show a few examples. So I have 2 sample apps. One is Training Wheels. It's just like one front end and one Redis backend. The other is the Docker Coins app with the Redis backend, but also web services, web front end, and worker. So with Training Wheels, if you want to deploy an ECS, so on ECS, you have new concepts. So each container on ECS is a task. Tasks have to be created from task definitions. And the task definitions are a little bit similar to the compose files, but not quite. But it's close enough so that you can translate, you can convert a compose file into a task definition. And that's exactly what ECS CLI is doing internally. So when you do ECS CLI compose up, that's the command that you do with it, it will take your compose file, it will transform it into a task definition, it will register that task definition into ECS and then create containers from that. Great. However, it will not work. It will not do builds. It will not work if you have a build in your compose.yaml file. So that's a good opportunity to use the build tag push recipe that I was talking about earlier. Here, if you do that kind of naively, like if you take your compose.yaml file with frontend and Redis and you bring it up, and then you try to scale with the CSCLI, what you end up doing is copy pasting your application multiple times. So you end up with like 4, 5, 10, how many you want them, copies of the same app with 10 different Redis things. So that's where we use ambassadors. And we do something that looks like this. Yep. So we start by deploying the stateful services separately from the stateless services. So the stateful service in that case is my Redis backend. So we put that somewhere. And then in our compose file, we will replace the Redis service with an ambassador pointing to the Redis service, so the gray Redis here, and then we bring up the stack on one machine. So that's what the Docker Coin application will look like on ECS when we start one instance. When we start a second instance, we're basically kind of copy-pasting the whole stack on another machine. If we put a third instance, we are copy-pasting the third stack, and that's it. Now, so that's a strategy for ECS. When we will go on Swarm, we will use a strategy which is based on network namespaces. And that's a really original, interesting feature in Docker and with containers, that you can have multiple containers that use the same network stack. So they are still different containers, they have different programs, different binaries, different everything, but they share the same network stack. So when you connect over localhost, you are sharing the same local host across everybody. On Swarm, the idea is that, okay, I will have my containers on 2 different machines, and my ambassador, so initially my application will start, and the web front end, if it tries to connect to Redis, there will be nothing. It will try to connect to the loopback address 127.0.0.1, and there is nothing here, so connection refused. Then I'm starting the ambassador, and I'm giving it the right address that was assigned to Redis. So now, when the web container tries to connect, it still gets connection refused because the ambassador is not configured yet. The next step is to inject the configuration into the ambassador. So to say, okay, ambassador, you are like, let's say, an Nginx or HA proxy TCP traffic forwarder, and you're going to forward connections to the actual Redis. And now, when the web server connects to the ambassador, the connections is transparently forwarded to Redis. And if I want to scale, that's what happens. I have like one instance of WW, one instance of Redis. I'm creating more instances of www. Then for each of them, I'm like adding an ambassador right next to it, and then I'm injecting the configuration into the ambassadors, and things work. Okay. So the equivalent thing on Swarm, so that will be, I'm starting with those empty Docker hosts. I'm starting all those containers all over the place. So at this point, each container is kind of trying to connect to the network services, but nothing works because there is nothing listening on the local addresses. Then I'm creating the ambassador containers, and at this point, each service is connecting to the ambassador, but the ambassador is doing nothing with the traffic. And then I'm adding the configuration, and now traffic flows correctly. And when I scale up, for instance, then I have new containers. So at this point, the nice thing is that I'm not breaking everything just because I scale up. I'm adding new containers, and yes, in the first stage, those containers are connected to nothing, but the rest of the app is still working correctly. Then I'm adding the ambassadors, configuring the ambassadors, and at this point, everything works. So at this point, we're like, whoa, that's a lot of rows here. What's going on? That's a lot of ambassadors. That's going to cost memory and everything. Research showed that ambassadors are super lightweight. The ones I use for my demos are based on HA proxy, and they end up using like 1 meg of RAM each. So that's pretty crazy low. And also one complaint is that sometimes people say, well, ambassadors are adding an extra hop. Before I was connecting straight from my web frontend to my database. Now I have the extra ambassador. So how do I get rid of that extra hop? In fact, you don't really have an extra hop because logically you have this extra HA proxy, but physically it's something local to your container. You're connecting over localhost, so the overhead that you're adding compared to the overhead of going to the machine where the database is actually running is really ridiculously small. It's even better because when you need an actual load balancer, very often you end up really having an extra hop, like you're connecting from consumer, load balancer, backend. With Ambassadors, you're doing consumer, load balancer, which is actually on the same machine of a localhost loopback, and the backend. So you end up saving hops instead of adding them. So what can we get if we add overlay into that mix? Well, first, as we said earlier, the simple case, like single backend, trivial service discovery is solved. And when we have multiple backends, we still get something easier because we can now name our backends, like if my service is RNG, I can have RNG1, RNG2, RNG3, and my load balancer can automatically detect those backends and configure itself automatically instead of having an external process that has to kind of inject the backend addresses. So we still need some kind of ambassador at this point, but it gets easier thanks to the overlay networking. Tomorrow, it will get even better because we will be able to have different concepts for the container name and the container host name. So the container name will continue to be that unique thing, so I can't have two containers with the same name. However, I can have multiple containers with the same host name, and in that case, when I'm in a container and I resolved RNG, it will resolve to all the IP addresses of the containers that are running the RNG service. So that means that there will be a DNS server embedded in Docker engine, and we will be able, for simple scenarios, to get rid of the load balancer and just use DNS round robin instead. So recap on what we saw. So the workflow with Compose gives us some kind of portability from my local dev environment to my remote cloud machines. Whether I'm using Swarm or ECS, it doesn't really matter. Actually, if I want to be fancy, I can even like have a ECS on Amazon and use a machine plus Swarm on physical nodes or some other cloud, and that way my Compose file remains my kind of universal infrastructure as code description for my application. There is a kind of slide like to kind of compare what we have with ECS and Swarm. Both give us really easy ways to provision clusters. If you are already like super deep into the AWS ecosystem, obviously you will prefer ECS because it's still in the ecosystem. On the other side of the coin, if you don't want to be super deep into the AWS ecosystem because you hate vendor lock-in, then Swarm gives you something that lets you go from one cloud to the other. But on the other side, it's like more in the Docker ecosystem. In both cases, you will need some extra tools to manage your builds, to process your Compose files, transform them. So that's same cost both ways. And in both cases, you need some extra work for plumbing and rediscovery. Future things that can be done. So app-specific ambassadors. So here, I'm sorry, I really have to find that slide. That's the one that I was in the beginning. I was like, what is this slide doing here? I think it was 25. Right, that was slide 25, tool belt. So a bunch of repos that I recommend to check out. Interlock, so that's something to listen to Docker events and automatically set up load balancers. Registrator, that's kind of the same thing, but instead of directly setting up ambassadors, it will put the containers in the registry, like console, for instance. Ahab by Instacart, that was released like last week, a couple of weeks ago. It will listen to Docker events and automatically call Python code to react to those events. So if you're like Python shop, that's definitely something you want to check. HA proxy console from Cisco Cloud. So that's something to like get something from console and automatically set up HA proxy from it. So if you combine registrator and HA proxy console, for instance, you get like a full-blown solution. Weave, so that's an overlay network, which is a little bit different from the one that is currently in Docker because it's using CRDTs, so it relies less on something like console, etcd, and so on and so on. Flannel, that's another overlay network. Pipeworks, that's the forbidden container network hacking tool that you shouldn't use, but if you really have to, it's here. Traffic, it's a load balancer that can automatically configure by using Docker events. Gorb, which is something to implement IPVS, a kernel-side load balancer for Docker. So that's just a bunch of tools. And now I have to go to the last slide for the question. So I'm going to try a different strategy for that. Yep. So bunch of links. Links to the ECS CLI tool, to all the code repos I was talking about, to the scripts that I was talking about. There are a bunch of videos with little demos. And again, if you look for DVO317, that was the session code of the talk at reInvent, so you can see like the full version of that talk with all the demos and code samples. Thanks.